All right. Workability. We've already heard from Tim about some of the issues that you can experience in the field. I'm going to try and set this up a little differently. We've been thinking about what are the things that we really need to make sure that a pavement is going to last forever. Now, we've done the whole performance engineered mixtures program, and the first phase of it was basically looking for the critical tests that would describe, will it survive the environment? And it was a deliberate decision, is that the thought process behind that would stop at the point of delivery. We're now starting to look, because having basically, we think, fairly successfully implemented that, there's still a lot of work to do, a lot of teaching and training to do, but it seems to be like a teenager. It's growing up and moving out of the house. I'm not in control anymore. Other people are doing it, and that's great. If only that stops him asking for money. Now we're looking at PEM version 2, or phase 2, which is, okay, it's come out of the back of the truck. What next? And the contractors in the room are going to be really irritated when I say, how can the contractors foul it up on the way through? You know, I can deliver a perfectly good mixture, but it still can get treated badly on the way through. And that's going to be the focus of the next phase. And that will include the things that I've highlighted in the yellow box. I've got a 40-minute presentation built around the slide. If anybody wants it, come and talk to me over lunch. All right. But for today, we're going to focus on the stuff in the yellow box, the workability, the air void system, as it's affected by the construction process, uniformity. And the part that I'm focusing on is what's happening with vibration. And again, Paul is going to follow up with some more detail about what we've been doing. Interesting that this session, I didn't know what Tim was going to talk about, but I was in a meeting with a whole bunch of FAA consultants, contractors, staff, high-end gurus, people who know what they're talking about. And they talked about the fact that one of the big issues behind FOD is that you got to get the coarse aggregate tied up in the corner of the slab so that you minimize the amount of material that can break off under traffic loading. And there was a lot of discussion about, we got to get that aggregate right up there in the corner. I don't argue with that. And therefore, we have to have the right slump. And in the end, I had to spend 20 minutes with them going through a version of this PowerPoint saying, slump ain't it. Slump doesn't tell you about how the aggregate's going to get up in the top corner. It's how the mixture responds to vibration. And when I raised that, they were, whoa, never heard of this before. But the mixture in a slump test doesn't have any energy being put into it. Mixture going through a slipform paver has a whole bunch of really powerful vibrators completely changing its performance. And that's what we've got to get our heads around. Understanding how a mixture is moving and responding to vibration energy. And if Paul doesn't say it, I'm going to say it. The vibrators can completely foul up a mix. And we've got to figure out, how do we make vibrator-proof mixtures? Or how do we tune the vibrator to the mixture and the materials that we have? Let's start talking to each other. Break down the silos in that conversation. So then we start talking about rheology, and I'm very glad Clarissa is not in the room because she actually knows what she's talking about. But you know, when you talk about rheology, it's not just one parameter. There's two parameters. There's the yield stress, the energy it takes to get it moving. And then there's the viscosity, the energy it takes to keep it moving or to accelerate it. And we need to understand the response of our mixture to both of those. Now, many, many years ago, when both Clarissa and I were still young, I went to her and said, we need to do rheology of paving mixtures. And she lay on the floor and laughed at me and said, slipform paving is not a liquid. It's not the right, rheology doesn't work, go away. So I crawled back in my hole, thought about it for quite a long time. And about the same time, Taylor was working on the box test, and I was working on the V-Kelly test, and we're still starting to figure out the response to vibration. All right, so yield stress, viscosity, regular concrete, slipform, paving slipform concrete's up here. It's got ugly viscosity, and it's got ugly yield stress, and that's what we want for the edge slump part, right? But when it's inside the paver, we want it to move like soup. And so it's the energy that's changing those properties that we really need to start understanding. Now we can understand, this is taken out of the literature of how silica fume, other products, add mixtures. If you're at a given place and you add one of these materials, the graphic shows us how these materials change their behavior. When we put in energy, it starts going back towards the origin. How much? How fast? What happens when you turn the vibrator off? Does it keep moving? Yes. That's that magic property called thixotropy, which for 11:30 in the morning is pretty easy to pronounce. All right. So we want to remove unwanted air. We want to get leveling. We've got to reduce the yield stress and the viscosity. We want to get the big bubbles out, and we want it to move. That's what we're doing with vibration. It's complex. There's a lot of variables in there. With a vibrator running, you're setting up energy going in a circular fashion. It causes the air bubbles to float out. It causes water to move sideways, and it causes the coarse aggregate to rotate. How much? When? How do you measure it? That's the part we still don't know. All right? Good vibration means no segregation, no air bubbles. What we're lacking is the understanding of correlating the vibrator parameters, energy, frequency, amplitude, duration, blah, 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 with the mixture. Admixture effects, different types of admixtures, water-cement ratio, fly ash and silica fume and fly ash content. All of these are complex in their own right, and we're trying to figure out how do we get these two different worlds to mesh. We started off this exercise with a very quick and dirty little exercise. We built a little box, and I got a device that measures vibration energy. And we put little steel rods at different lengths. There's the longest one on the top. The next one was just here, a couple of inches down. The next one was the third in. Filled it up with concrete, stuck a poker vibrator in here, and then measured how much energy was reaching those the tips of those rods. So we got a sense of how much energy was being transferred through the mixture and how it changed over time. We then pulled the cores out of these things and measured a whole bunch of other properties. We did a boatload of testing, and I'm not going to go into detail. All of the information is in an ACI, I think it's in the materials journal. If anybody needs a link, talk to me. But all of the data is published. I'm not going to relitigate all of that. But what we did learn is that increasing the air doesn't actually change the amount of energy you've got to put into it. It also didn't change the amount of energy lost over distance. What we did clearly show is that if the tip of the vibrator is here and it's parallel with the shaft, we were very clearly able to show air moves up and sideways. And even more interesting, water is moved up and sideways. And I think Paul's going to expound on that a little bit more. But moving water is actually kind of intriguing and kind of new in our thought process. We're also moving air up, which is a little surprising because the number crunching is telling us big bubbles will move pretty readily. Small bubbles, it's a struggle to get them to move. And that's a good thing because we want them to stay in place. Less energy is transferred in a drier mixture. So the range that the energy reaches, or the range that the vibrator reaches, is less in a dry mixture. So again, if you're dealing with a bone dry mix, you may need to put in slightly more vibrators. All right. If you increase the frequency, the amount of energy goes through the roof. And that's precisely why contractors do it. Right? The mixture's looking a little bony and doesn't move around and you're not getting the finish. First, the only thing you can do is crank up the frequency because you can't change the amplitude that's built into the system. And so we're putting a whole lot more energy into it, but that's not necessarily a good thing to do. All right. Again, water moves everywhere we go. So we're starting to develop tools. This is the V Kelly device. It's a Kelly ball, 6-inch diameter ball with a vibrator mounted on top of it. and we measure how quickly that ball sinks into a mixture. With the vibrator off, that's a direct correlation with slump. With the vibrator on, now we're starting to get to understand the viscosity side of that rheology equation. And we're starting to figure out how do we correlate this with the vibrator and the mix. We've got a pool fund request out there at the moment. If anybody wants to give money, I can tell you where to send a check. We're harassing the states right at the moment to start supporting this work. But just to get a better understanding of how these two systems play with each other, so that at the end of the day, Tim is out of work. Yes. And I think I've got us back on time. Yeah. Any questions? Anybody want to argue? Come on, Tyler, bicker with me.
I speak for the same level.
Good.
Do you have any questions?
Nothing online.
Peter, can you explain a little bit about that? How do you check the water movement?
Sure.
Can you repeat the question through the microphone, please?
I will do that. Yeah, I thought I was supposed to end at 11:30, but it was supposed to be 11:40. So, okay. That's why I blew through this really fast. The way we did this is we pulled cores out of that box. One right on the edge of where the vibrator was, and another one 6 inches in, another one 6 inches from there. And we did a very quick and dirty and ugly test I call the drop test. I stole it from Ron Sturm, who was a petrographer at CTL. Sorry, I forgot to repeat the question. The question was, how did we measure water movement? So we pulled these cores, split them in half, and you drop 10 microliters of water on the paste. And you measure how long it takes for that drop of water to soak in. Really dirty, totally unscientific, but it does very clearly show you differences across the sample. It's not an absolute test, but it does clearly show. And because it's got such a small footprint, it means you're not testing a whole 4x8. You're testing footprints of about the size of your fingernail. And so we were able to draw up these lines of the water got sucked in really slowly down here by the vibrator and got sucked in really fast in the top right-hand corner. So that was the approach we used to demonstrate that, yeah, water is moving. The theory being is that if the water got sucked in fast, the water-cement ratio must be slightly higher because everything else was controlled, including the curing and all of that good stuff.